Hello, this is a re-record of today's final lecture, continuing along in the final exam review packet, starting with question 11. So we have a compound known to be XO3 in its formula, where X is an unknown element. The compound is known to be 60.0% O by mass. What is the formula of the compound? Well, I'm just going to use what I know about percent mass, which is that the percent O, which would be 3 times 16.00 AMU, that this divided by the formula weight of the compound times 100% is the percent oxygen, which is 60%. I'm going to get rid of the percent and just call this a fraction. So 60% is 0.600 as a fraction. Then the formula weight of my compound will be 3 times 16.00 divided by 0.600, just solving algebraically for the formula weight. This gives me a formula weight of 80.0 AMU, which is the entire mass of the whole XO3 unit. So I just have to subtract the mass of 3 oxygens, and that leaves behind a mass of 32.00 AMU. And then I just go check in the periodic table for which of these elements has a mass of 32, and that's sulfur. So this would be SO3. Next question is looking at a compound that's percent carbon by mass is 87.7, percent hydrogen by mass is 12.3, gives us a molecular weight and wants us to determine the molecular formula. Our percent by mass data here gives us the empirical formula. So we'll determine that in step 1. And then step 2, we'll take the molecular weight, divide by the empirical formula weight to then determine the molecular formula. So we're going to do this problem in 2 steps. I think that's the intent of the problem, is that this is a 2-step problem. You could devise ways of taking the AMU mass times 87.7% for carbon and figure out how many carbon atoms that is. There are other ways of solving this problem, but I think sort of the way we intend is to understand how to get an empirical formula, then understand how with the molecular weight we can get the molecular formula. So the empirical formula, I'm going to start with the 87.7 grams of carbon. I know that's in ratio to 12.3 grams of hydrogen. I'm just going to convert these to moles. And then work this out here. So that's 7.30 moles of carbon, and then 12.2 moles of hydrogen. And these are the ratio of these atoms to each other. To get the simplest whole number ratio, let's divide by the smallest first. We got to divide by the same number to keep the ratio intact. So I get 1 mole of carbon in ratio to 1.67 moles of hydrogen. And what we want to think here is I'm going to multiply both of these by the smallest whole number. 2 doesn't work, still have a fraction, so I go by 3. Multiply them both by 3, then I get C3H5 as my empirical formula. And so this is the empirical formula. Its weight would be 12.01 times 3 plus 1.008 times 5. So this is has an empirical formula weight of 41.07 AMU. Then I just look at the molecular weight of 164.3, divide that by 41.07. This is equal to 4. So I have 4 units of the empirical formula in the molecular formula. So it's C3 times 4, H5 times 4. So that's C12H20. So the next problem is a stoichiometry problem. It's giving us 22.5 grams of calcium carbide, 22.5 grams of water. What I'm trying to think here is which one of these two might be the limiting reactant. I'm kind of leaning towards calcium carbide. Well, one, because I know it from doing it in class earlier, but also because I'm just thinking here, relatively high molar mass, so I'm probably going to have a relatively low number of moles. I have what looks like a lot of water, but I need, 2 moles of water. So I'm thinking calcium carbide is probably my limiting reactant. If I pick correctly, I save myself a dimensional analysis step. So I'm going to work out the number of grams of water that react in the reaction with 22.5 grams of calcium carbide. And I'm going to use dimensional analysis. The molar mass, 40.1 plus 12.00, 12.01 times 2. This is 64.1 grams per mole of CaC2 times the conversion factor for every 1 mole of CaC2. According to the reaction, we need to react 2 moles of water with it. And 1 mole of water has a mass of 18.02 grams. So this means that I'm going to have 12.65 grams of water consumed in the reaction, not remaining, but consumed. So I have 22.5 minus 12.65 grams of water remaining. That's 9.9 grams of water remains. So CaC2 is my limiting reactant, 9.9 grams of water remains. And I think I circled the wrong answer on the answer key, so I'll have to go fix that. But if you look at the answer key, the limiting reactant is calcium carbide, and then the water is what remains, 9.9 grams of water remains. Questions here, getting into chapter 4 topics, calcium chlorate. This is a water-soluble ionic compound. I know it's not on our solubility chart. I think on the exam I wrote, it was on the solubility chart. So just imagine you'd be told that this is like a soluble compound. You can kind of pick up that it is because there's no choice of 0 moles. If it's insoluble, the answer would be 0. If it's soluble, the answer is going to be it forms calcium 2 plus. The chlorate ion stays intact as ClO3 minus. So we get this ion plus 2 of this ion. So I get 3 moles of ions in this solution per mole of calcium chlorate. So I have 2.5 moles. I get times 3, I get 7.5 moles of ions into that solution. Question 2, which compound partially reacts with water? Ammonia does because we make ammonium and hydroxide ion. We just do this partially, that's why it's a weak electrolyte. So NH3, weak electrolyte, weak base. Base because we're making some hydroxide ion. Acetic acid in water partially dissociates to acetate and then H plus ion. And so the formation of H plus is what terms this to be an acid, and it does this partially, so this is a weak acid. So it's a weak acid, weak electrolyte. And so both compounds A and B partially ionize in water because they're both weak electrolytes. Weak acid for acetic acid. So our weak acids are all the acids we learned how to name as acids that aren't one of the 7 strong acids. So just a reminder of our strong acids, HCl, HBr, HI, note no HF, HClO3, HClO4, HNO3, and then the first H from H2SO4. So just the first hydrogen off H2SO4. So those are our strong acids. All the other acids we learned how to name are weak acids. And then anything that we don't put the word acid on with nomenclature is not an acid in water. So if you had something like methanol, this is a non-electrolyte. Not acidic, not basic, doesn't release hydroxide ion, doesn't release H+, just stays intact as CH3OH molecules in water. Same thing with ethanol. So when ethanol is in solution, it's best termed a non-electrolyte. That's not an acid or base. If you're an acid or base, it has to be some kind of electrolyte, just weak if it's partial. If it's a weak acid, it's a weak electrolyte. If it's strong acid, strong electrolyte. Okay, so this question here is asking about the molarity of a solution from a titration. This is a problem that we skipped. So this isn't something to worry about for the final, or wasn't something we worried about for the midterms. So we didn't cover titrations in chapter 4. We also didn't cover activity series, using it to solve problems of which metal oxidizes in a solution of some other type of metal. So that out of chapter 4 we also skipped. So these are 2 topics out of chapter 4 that if you see topics related to these on practice quizzes, you can skip those. All right, question 20 out of chapter 5. So we have 4.75 grams of magnesium reacting with excess oxygen. According to this reaction here, the delta H is minus 1204 kilojoules, but this is, per 2 moles of magnesium. It's per 1 mole of oxygen, per 2 moles of MgO forming. So the coefficients in these reactions here are assumed to be moles to give us this delta H. We know that if you cut the coefficients in half, if you had Mg plus half a mole of oxygen form MgO, that this delta H, we know this would be minus 602 kJs. This would be 602 kJs per 1 mole of magnesium. So 1204 per 2 moles is the same as 602 for 1. It's the same ratio. And that's important so that when we're solving for the number of kJs here, let's say our Q reaction is what we're solving for. We take our 4.75 grams of magnesium, go 24.3 grams per mole of magnesium, that we do the minus 1204 kJs per 2 moles of magnesium. I need this 2 moles here. This isn't going to work out right because it's 1204 kJs per 2 moles of magnesium reacting. If only 4 moles react, that's 0.0437 moles of magnesium. 0.0437 divided by 2 times 1204. This works out to be negative 118 kJs. The reaction's exothermic, loses heat, so 118 kilojoules is released by this reaction. So exothermic reaction, heat is released. So heat's released by the reaction to the surroundings. If we had this reaction taking place in water, which doesn't look like it's in water, but let's say it's in water, then the solution temperature would increase. The temperature of the solution of the surroundings would increase. Whenever we're tracking the temperature of a solution, it's always the surroundings of the reaction. That'll come into play in our next question here. So the next question, let's look at NH4NO3 being added to water. We did this in class. We took calcium chloride, added it to water, which is exothermic, has a negative delta H. And then we took ammonium nitrate, which has a positive delta H. And this one was our cold. This was our cold pack, because the endothermic reaction absorbs heat from the water that we poured into the reaction, absorbs the heat from us when we touch it. So this leads the temperature of the solution to drop. So which statement is true? When ammonium nitrate is dissolved in water, the solution, which is the surroundings of the reaction, are going to drop in temperature because the heat was absorbed by the reaction. So remember, Q reaction, negative Q the surroundings. So if the reaction has to absorb heat, then it comes from the surroundings heat. So the surroundings heat is being lost here in the process. So the temperature of the surroundings drops, it's losing heat because the reactants to form products are absorbing the heat. So the solution drops in temperature because the reaction absorbed some of its heat. So this problem here is a calorimetry problem. We have 3.5 grams of ammonium nitrate being added and dissolving in 125 grams of water inside of a coffee cup calorimeter. The main idea of a coffee cup calorimeter is just an insulated cup where a reaction can take place where heat cannot be exchanged with the outside of the container. So there's no heat being exchanged with the outside of the container. I don't know what symbol I'm trying to draw here. I'm trying to draw, we have shown some of these symbols here for heat, that the idea is that there's no heat being exchanged with the outside of the container, only that all the heat generated or absorbed from the reaction is coming from the cup itself. Okay, so ammonium nitrate added to water dissolves in the coffee cup calorimeter initially at 25 degrees C. What is the final temperature of the inside of this calorimeter? If the enthalpy of solution of the compound is 25.7 kJs per mole that we showed on the previous slide, and then we're given the specific heat of the solution is that of water, and then that the heat capacity of materials have a negligible heat capacity, meaning that we're not worried about the materials absorbing heat, it's just the heat of the solution as it relates to the heat of the reaction. The heat of the reaction is the opposite in sign of the heat of the solution. The solution is the surroundings of the reaction, and the solution is described by an MCS delta T. And then our delta H, which we have given to us, 25.7 kJs per mole, relates to the Q reaction. So I can get my Q reaction by taking the actual amount of reaction I have taking place, 3.5 grams of the reactant, which is our limiting reactant, the only reactant, dissolving into water. So I'm going to do the conversion over to moles. And then I'm going to use my 25.7 kJs per mole. So my moles of ammonium nitrate cancel, my gram cancels. And then I'm going to do one more step, which is I'm going to convert to joules, just because my heat capacity is in joules here. So I might as well just go ahead and convert that now. And this works out to be, the Q reaction ends up being plus 1,123 joules, good to the third sig fig, because of 3 sig figs here. Okay, so what I want to do now is I want to plug this in here and solve this equation here for delta T. I know my mass of the solution is 128.5, and my CS is the value that was given. So my delta T is going to be 1,123 divided by negative 128.5, the mass of the solution, grams, and then 4.184 joules per gram Kelvin. So my grams cancel, my joules cancel, my 1 over Kelvin flips up. So my delta T ends up being equal to negative, from here, negative 2.09 degrees C. So I have two ways of knowing that the temperature should drop. One is it's endothermic. The heat's coming from the solution, so the temperature should drop like we talked about on the previous page. And then I also correctly did the arithmetic, so I get the negative sign here. So my delta T is minus 2.09 degrees C. Now, if you're confused on how I went from Kelvin to degrees C, let's knock that out here. So if we go from 25 to 22.9 degrees C, so this being my final, this being my initial, 22.9, 25.0 initial, oh, sorry, let me flip this actually. If I go 22.9 is my final temperature minus 25.0 initial for final minus initial, then that gives me minus 2.1 degrees C. So 22.9 would be the answer to the question. Circle it real quick. But then let's also address the fact that we could have converted 25.0 to Kelvin. That would be 298.15 Kelvin. 22.9 over to Kelvin. 273.15 added to it is 296.05. Good to this placeholder here, but I do 296.05 minus 298.15. I get 2.1 Kelvin. So if I convert these to Kelvin and take the difference, I get the same difference in temperature. So I have to be a little careful here. A little careful to recognize when I get my delta T was 2.1 Kelvin, it's 2.1 degrees C. So my temperature drops by 2.1 degrees C to 22.9 degrees C. I don't need to, I've occasionally seen students change this to, Kelvin or degree C or whatever. Take 2.1 Kelvin, convert it to degree C, which would be like negative, whatever that would be, 271 Kelvin. That's not right. Delta T in degrees C equals delta T in Kelvin. Okay, so that's an important concept that we don't need to make a mistake on a simple conversion and calculation of temperature. If you want to get caught up on Kelvin, just convert 298 or convert 25 degrees C to Kelvin, take your difference, convert it back to degrees C, you'll get precisely 22.9 degrees C. Okay, so that's our calorimetry problem. I think it's worth noting or reminding you guys that a lot of times we give you the information to calculate delta T. So we take delta T times Ts times the mass. And so we solved this problem here a lot where we get our Q reaction, negative MCS delta T, and then we have to solve for delta H, often by taking the Q reaction and then dividing by the limiting reactant, and usually converting it to moles to get kJs per moles. Is a photon absorbed or emitted when a hydrogen atom transitions from n equals 5 to n equals 2? So n equals 5 certainly is going to increase in energy. N equals 5 to 2 is going to lead to a release of energy. Energy is increasing upward, and so therefore energy is decreasing downward. So energy is released by this atom, and the energy is released by the emission of light. So a photon of light is created, and so we have light being emitted. And then one thing that I talked about in class today, and we talked about this previously, is that this should be in the visible region because the 6 to 2 through the 3 to 2 transitions were the visible transitions for hydrogen, and so that should be a visible photon. This is a UV photon. The 304 doesn't make sense for a 5 to 2 transition for hydrogen. Now, if we wanted to solve and precisely work out the 434, we could do one of two things. We could calculate the delta E by taking the energy of the final state of 2 minus the energy of the final state of 5. This is the atom losing energy. This should be negative. And the energy lost by the atom is given to the photon. So the E photon is the negative the delta E for the H atom. So it's a positive amount of energy given to the photon. And then the photon energy is just equal to hc over lambda. So we get our photon energy, set it equal to hc over lambda, solve for lambda, and that's how we could solve the problem that way. We could also plug into the equation 1 over lambda is equal to the Rydberg constant, times something related to the n values. So you could look this equation up on the chart, apply it, solve it, and accordingly get the wavelength. The Rydberg constant's on the equation sheet, as is this particular equation. So you can look at that equation and use it accordingly. So a few different ways we can think through this problem. I would expect more of a conceptual problem than a mathematical problem on this topic, looking towards the final. So I don't think necessarily working through the math will be something you have to do in the final, but thinking through conceptually, probably something worth considering. Chromium has this anomalous configuration. It should have been a 4s2 3d4, but it just moved one of the s to the d subshell. You don't have to have memorized which atoms do this, but chromium happens to do it. So we get a 4s with 1 electron, and then a d subshell with 5, so we get 6 unpaired electrons for chromium. How many orbitals are there in a 5p subshell? So the 5p subshell just contains the 5px, the 5py, the 5pz. So we just get these 3 orbitals here. Now, why you get the 3, you might go back to, well, n equals 5 for this orbital here, but the L is equal to precisely only 1. The 5s is L0, the 5d would be the L2, the 5f would be the L3. So the 5p is just the case where we have L equal to 1, and the range of m sub L's here is -1, 0, +1. This is our 3 orbitals here. That's why we get 3 orbitals. So 3 5p orbitals occupying the 5p subshell. What about an orbital with an n of 4, an m sub L of -2? What is the range of possible angular momentum quantum numbers, L, for this orbital? So the range of L for n of 4 would be 0, 1, 2, 3, but the L of 0 and 1 couldn't have an m sub L of -2. The first time we can have an m sub L of -2 is L2 and also L3. So for L2, we go -2, -1, 0, +1, +2. And then for 3, we add the -3 and plus 3. And so for the L 2 and 3, we get the possibility of having an M sub L of minus 2. So kind of just a word problem here for this question. Effective nuclear charge increases from left to right, and it also slightly increases from top to bottom due to the increase of the core electrons and their lack of an ability to screen as they become larger. And so it's going to be highest, if you think of our periodic table, it's going to be highest in the far right. So iodine here is going to have the highest effective charge of these choices. The lowest effective charge would probably be, of these choices, probably rubidium. So probably something on the left side of the periodic table being relatively low. Atomic radius is decreasing left to right due to the increase in effective charge. And then it's increasing top to bottom just due to electron repulsion, having larger shell orbitals being used. And so our largest atomic radius, if I reconstruct a little periodic table here, is that sodium should be the biggest. Sodium's bigger than lithium, lithium's bigger than nitrogen, sodium's bigger than sulfur and chlorine, so sodium's the largest. If you wanted to identify the smallest, nitrogen's probably the smallest. It's probably smaller than sulfur and chlorine. Can we definitively say that, though? It's a little tricky comparison because chlorine's pretty small, too. So not a great choice. If we had fluorine here, fluorine as a choice would be a better choice for if we wanted to identify the smallest orbital. Or, excuse me, the smallest atom. Ranking based on size here for the ions, we just have to inspect the ions to notice that they all have 10 electrons. So magnesium 2 plus, magnesium has 12, lost 2 has 10. Sodium should have 11 electrons, lost 1 has 10. Fluorine has 9, gain 1 also has 10. And so the key here are the proton counts. That as the proton count decreases with the same kind of electrons, the ion grows larger. So F minus, biggest, magnesium 2 plus, the highest charge, smallest, sodium in the middle. What general trend, proper explanation for the first ionization energy for top to bottom in a column? What is that trend? Generally, we get a slight decrease from top to bottom. We get a increase from left to right with a periodic inconsistency. You might remember the NP1, the NP4 have slightly lower ionization energies than you would expect, but attraction to the nucleus should increase from left to right due to the decrease in size and increase in effective charge. But from top to bottom, we have two competing trends. We have the atoms become bigger, but then the effective charge becomes higher. The effective charge becoming higher would predict a higher IE. The size increasing predicts a lower IE, and it's this decrease in ionization energy is the general trend that we observe for most of the elements on the periodic table. So it's the size increase that's allowing us to predict this trend most often. So IE1 tends to decrease from top to bottom because atomic size increases. Which ion below contains the most unpaired electrons? So what we want to think about for an atom like zinc, to get zinc 2 plus, you might think, well, what's the neutral atom? That would be argon 4s2, 3d10, and then I'm losing the s electrons first. I'm losing the electrons first. So we lose electrons from the highest n orbital with the highest l orbital first. That's a fancy way of saying lose the largest electrons first. So we're losing the 4s2 electrons before the d electrons, so zinc 2 plus is a 3d10. All the electrons would be spin paired. Cobalt 2 plus is an argon 3d7. Lost its 4s, so we're just losing the 4s here. Iron is an argon 4s2, 3d6, so iron 2 plus is just a 3d6. Manganese is an argon 3d5. And then calcium is just the argon configuration. It was a 4s2, lost the 4s2. So calcium has no unpaired electrons. Manganese is best because, or the answer to the question, because we have all 5 of those electrons spin unpaired. So we get 5 unpaired electrons. I only get 4 for iron because the 6th electron has to spin pair. I only get 3 for cobalt. So I have 3 unpaired electrons for cobalt. Consider the following ionic substances and arrange them in order of decreasing lattice energy. So lattice energy decreases when the ions become larger. As ions become larger, they decrease in lattice energy. And then as lattice energy increases, or excuse me, let's keep with lattice energy decreases. If lattice energy drops, that leads to a lower melting point too. Melting point ends up coinciding with lattice energy for ionic compounds. And so anyways, so to decrease by decreasing lattice energy means the lowest lattice energy will have the largest ions. So with the biggest, Ki is the biggest, sodium iodide's in the middle, lithium smaller than sodium, chloride smaller than iodide. So lithium chloride's the greatest, sodium iodide in the middle, Ki the lowest. Sig fig question here. If I do this arithmetic here, 2 numbers multiplied together, divide by a number. Let's look at that first. So the order of operations would be 7.045 times 0.545. That quantity divided by 0.0042. So multiplication division, this number here would be rounded to 2 sig figs, 910. So I take 910 and then 6044, good to this placeholder. And so my result here is going to be rounded to the tens placeholder. And so I end up getting, I see. I did put it in my calculator wrong. 6044 plus 910 is 6,954. So I round this to 600,950 with 3 sig figs. So higher value placeholders where we round the result to. So 3 sig figs. This is the final problem we looked at in class today. So this problem here looks at, or is asking, which one of these figures best represents a mixture of 2 different molecules. And so figure 1 shows 1 molecule. So that's just 1 molecule. So that's not the answer. Figure 3 shows 1 molecule, so it's not the answer either. That's just 1 molecule. So we need 2 molecules. Figure 4 is wrong because these are atoms, not molecules. So all a molecule needs to have is 2 atoms. So like H2 is a molecule. H2O equals molecule. Technically, NaCl is not a molecule. It's a compound. It's an ionic compound, so it's a little weird. But I just need 2 or more atoms connected together. They can be the same element, though. So there's nothing wrong with this being maybe something like H2. That's definitely a molecule, and this is a different molecule with a different shading. So there's my 2 molecules. So 2 different molecules represented in figure 2. Okay, so I'm going to prepare a second video over the remaining, I think, 10 pages of problems. So I'll put that video up later this afternoon. But for now, these are the problems that were presented in class today. And so with this, I'll just say, thanks to those who have, been watching these videos. Thanks to those who've, interacted with the class. I wish everybody good luck on the final exam and on any other finals that you're taking. And I really enjoyed teaching this class. Hopefully you learned a fair bit about chemistry in the process. And good luck with the final and hopefully future chemistry classes that you take. So good luck to you guys. See you around.